This is one of the standard one-dimensional problems in stationary states. So here we study the behavior of the system independent of the time. So here we are defining a potential where for x less than 0, v is 0, x greater than 0, v is equal to v0. So there is a potential step with finite height. Okay, and a particle is incidenting on this with energy less than v0. Then will it cross the barrier? Will it enter the other region, or will it get reflected back completely or not? That's what we need to study here. So classical mechanics predicts that the particle will be stopped or completely blocked by this potential here. But whereas in quantum mechanics there may be some modifications or corrections due to uncertainty. So that part we will see in detail here. So here I am taking this as a potential. For x less than 0, v is equal to 0, and for x greater than 0, v is equal to v0. Now the Schrodinger wave equation for this system. Schrodinger wave equation in stationary state Schrodinger wave equation. This is a Schrodinger wave equation. So for x less than 0, what do you get? D square 7 x square plus 2m e by h bar square psi is equal to 0. So here is the total energy. V is the potential energy. And I call this quantity 2m e by h bar square as k square. So now the solution of this equation is what? We can have exponential solutions or even sine cosine solutions, and for the time being I am considering exponential solutions. Psi is equal to these are the two possible solutions. Since I don't know which one contributes, I am taking the combination of both. So now we have to see the real system. Here this part, if we include time factor comes as e power minus I omega. So ikx minus omega t, and this is minus ikx plus omega t. So time factor comes as minus IET by h bar or minus I omega t usually. So you see this first part is kx minus omega t and second part kx plus omega. And this part usually the phase remains constant. I mean, if you raise the time factor to keep the phase factor constant, you have to raise the opposition also. So, if time rises in a positive direction, position also increases in positive direction. So, this term represents a forward moving particle. Whereas in this case, if time rises in positive direction, x has to rise in negative direction to keep the number constant. Okay. So, this is a negative going wave, e power minus ikx, and e power plus ikx is forward moving wave. So in this region, region 1, the system is saying there are two possibilities. One is a forward moving wave, another is a backward moving wave. These are the two possible solutions, and it is our choice to keep both or consider any one of those. So here, the system allows the possibility of both. Because there is a wave incidentally, and a part may be reflected or completely it may get reflected. So, in region 1, we have a forward moving wave, also backward moving wave. So, we have both the possibilities. Okay. And coming to region 2. So, in the region 2, the Schrodinger equation becomes this. So, in region 2, V is equal to V0 and E is less than V0. So, what happens to this? D square is equal to x square plus 2 by h bar square E minus V psi. E is less than 0, so we get a negative number. So d square psi by dx square minus k prime square psi. So here k prime square is so here check these solutions. If you differentiate this with respect to x twice, for the first derivative you will get plus ik, next one ications, ecoregions. So, if you double derivative this function, what do you get? D square sided dx square is equal to minus k square. Plus ik and plus ik twice. So here we need to get plus k square. Upon double derivative, we should get plus. Okay, so the possible solutions are, I can write it like psi is equal to c e power k prime x plus d e power minus k prime x. So there will not be any I factor. If you double derivative this, you get plus k square. So d square psi by dx square is k prime square psi. So these are the possible solutions. And we need to fix whether both exist or any one. Right. So in the first region, we are considering there is an incident wave and there is a reflected wave. And in the second region, if at all if the wave enters, there will not be any reflected wave. There is only a forward moving wave. And that too, I should say it is a decaying wave. It will not enter at all. There is a certain probability of penetration. So, this becomes no exponentially rising wave. Only falling wave. So in the second region, only exponentially falling wave exists. So the solution is psi is equal to d e power minus k prime x. So now we have to calculate transmission coefficients and reflection coefficients. Okay, I mean how much portion is getting reflected, how much portion is transmitting, that we need to calculate. Okay, so the current density, what is this current density equation? H bar by 2mi psi star del psi minus psi del psi star. This is the current density equation. And we have to define transmission coefficient and reflection coefficient. So transmission coefficient is transmitted wave. So I should call it as psi transmitted. So J transmitted by J incident. And the reflection coefficient as J reflected by J incident. The transmission coefficient and reflection coefficient are defined like this. This is the ratio of transmitted current by incident current, and reflection coefficient is reflected current by incident current with a modulus. So first of all, we need to calculate this J transmission, J incident, and J reflect. J incident. So A e power ikx is the incident wave. So psi incident is equal to A e power ikx. Then what about J incident? Is h bar by 2mi psi star A star e power minus ikx del psi ik A e power ikx. A star e power ikx and derivative of the other ik times, here it is a minus e power ikx. A star e power minus ikx, ik times e power ikx minus A e power ikx derivative of conjugate minus ik times A star e power minus ikx. H bar by 2mi modulus A square to I. So it is h bar k by m modulus h. So in the same way, J reflected. So psi reflected is what? B e power minus ikx. So J reflected will be h bar k by m modulus b square. Will there be a minus? So we get a minus here. finally we are taking a modulus here, so no issues. And then transmitted wave. So psi transmitted is d e power minus k prime x. And there are no imaginary terms. So the current transmitted becomes here. Because psi star and psi will remain same, so you get a 0. So overall reflection quotient is 0. Sorry, transmission quotient. And reflection quotient is what? Modulus b square over modulus a square. So here the transmission quotient is 0 and reflection quotient we got in terms of B and A, these quotients, C and D quotients, which we don't know as of now. So we need to get those values. And technically this, since T is 0, R should be 1. So we need to verify that. Point number 1, the reflection quotient will become 1. And if you see the transmission probability, P transmission modulus psi transmission square is non-zero. There is some exponentially decaying probability of observing the particle in the second region. And the transmission quotient is 0, means there is no transmission current in the second region, but there is a transmission probability into the second region. That means the particle instead of reflecting at the boundary, it may enter the region and come back. So there is a exponentially decaying probability in the second region, but there is no current in the second region. Okay, so now we need to get the values of A and B. So that is our next task. So the wave functions we got here is psi is equal to A power ikx plus B power minus ikx. Psi transmission is equal to D e power minus k prime x. Right? Here it is x is equal to 0. So we have to apply the boundary conditions for this wave function. What are the boundary conditions? Psi at x equal to 0 is equal to psi transmission at x equal to 0. Dou psi by dou x at x equal to 0 is equal to dou psi transmission by dou x. These are the two boundary conditions. Wave function and its first derivative must be continuous across the boundary. So we have to substitute x equal to 0 and equal to, if you substitute x equal to 0, this becomes a into e power 0 plus b into e power 0 is equal to d into e power 0. So a plus b is equal to d. And differentiation. Ik times a equals 0 minus b equal minus 0 is equal to differentiation minus k prime d equals 0. This equation becomes ik times a minus b is equal to minus k prime times b. So what we have got here is d is equal to a plus b, d is equal to minus ik by k prime a minus b. So here we need to get the relation between a and b, and we don't need d. So get the value of d from one equation and substitute in the other one. So what do you get? A plus b is equal to minus ik by k prime a minus b. Somehow we need to get the ratio a by b or b by a. So we have to write b is equal to some function of a. Then you have to get all the values of b to one side. b minus ik by k prime b is equal to minus ik by k prime a minus a. B into 1 minus ik by k prime is equal to minus a into 1 plus ik by k. So if you remove the minus, it's up to you. Otherwise also you can keep it like that. So now what we need is b by a minus 1 plus ik by k prime by 1 minus ik by k prime. So we have to take modulus square of this. means you have to multiply this number with its complex conjugate. So how to do that? So we can't just write or we can't just replace plus I with minus I, and because one number is in numerator and another is in denominator, you can't do that directly. Yeah, rationalization. So this is minus 1 plus ik by k prime, 1 plus ik by k prime. So multiplying with 1 plus ik by k prime on both numerator and denominator. So this becomes a plus I by k minus I b, a square plus b square, 1 plus k square by k prime square. So b by a is one plus 1 minus k square by k prime square plus 2i k by k prime. By 1 plus k square by k prime square. So now I have to take a complex conjugate of this and multiply with this. So modulus b by a square is so minus will become plus, otherwise keep that. 1 minus k square by k prime square plus 2i k by k prime and 1 minus k by k prime square minus 2i k by k prime. By 1 plus k square by k prime. So a plus ab, a minus ab, a square plus b square. So what do you get? So modulus b by a whole square is minus k square by k prime square square plus 4k square by k prime square. By 1 plus k square by k prime square whole square. So modulus b by a whole square is k square by k prime square whole square. So now do one thing. Just replace plus and minus here and multiply. So that brute force method works. Let's check. Looks like a lengthy derivation. Just wherever you see plus I, replace it with minus I and multiply. Check what you get. So what I am doing 1 plus ik by k prime 1 minus ik by k prime 1 minus ik by k prime 1 plus ik by k prime. What? Get one direction. Need to. We'll see later. In next problem also, if that works, it's okay. Done.